Growing Plants in Space by Mason Kummer. This is a topic I'm incredibly passionate about and I'm excited to share with you. The topics we will discuss are the need for space agriculture, environmental conditions in space, system developments and applications, government versus private sector, the training required, and the application of space farming on Earth. By 2050, it is anticipated that the world population will go up to 10 billion. In order to sustain all these people, we will need to implement more sustainable and efficient systems. This is something that space agriculture can teach us. In space, physical nourishment is pertinent. Our astronauts need to be able to eat healthy so that they can have all their proper body functions and that they can operate at their best. Further, they need to be mentally nourished, and plants have shown incredible benefit to crew morale boost, as well as it's given them a connection back to feeling at home. It is completely unfeasible to bring all the food required for a long-term mission. This is because it would take up too much space and weight. This means that the food needs to be grown locally on site. The environmental conditions in space are seen as very different from that on Earth. To touch on some of the stressors, we can see microgravity effects and radiation exposure. To touch on gravity issues, in a zero-gravity environment such as the International Space Station, we can see that the water tension, the surface tension, is so high that it forms a globular-like shape. This can pose some significant challenges to root uptake of water and for aeration. However, this can be mitigated as seen later. Plants are also confused about the growth of where to grow, their direction, and this can also be mitigated through things such as LED lights and anchoring. Further, reduced atmosphere and increased radiation in space show that we are not able to grow in a solely outdoors environment. This is also demonstrated by the temperature challenges. In this diagram, we can see that there is water on the moon. This is where we would want to put our controlled environment agriculture situation. However, there is such a great temperature change here that it also poses challenges where we need to have an insulating barrier between our controlled environment and the outside space. Lighting challenges, as mentioned, the LED lights are required to supplement lighting. In the event that we have an underground system or a surface system, the insulation, having the light come through, will end up taking away from the natural lighting, so it will need to be supplemented. The need for controlled environment agriculture is a must. And like I mentioned, heavily insulated system is important. Having heavy automation or regulation is important to manage time and the potential for underground systems. Integrated pest management as well is an important concern when growing in space. We want to start with as minimal pests as possible. It's unfeasible to sanitize everything, so having an integrated pest management approach would be the best possible solution. Current system developments and applications. The Vegetable Production System, VEGI, is a system created by NASA to operate on the International Space Station. There are 6 pillows of a clay-like media with wicks inside. As mentioned previously, the challenges of uptake of water. The wicks allow for the water to be taken up slowly and not to surround the roots, preventing breathing. Next, the Advanced Plant Habitat is a fully enclosed system, separate from that last system, which was open. This system is completely remote controlled from the Kennedy Space Station on Earth and allows for all of the inputs to be fully regulated and monitored, all from Earth. The only things that the astronauts would need to do would be add water and harvest. The Eden ISS is an incredible system, not currently in implementation, but is being researched and explored in the Arctic. It features 2 sections, the Future Exploration Greenhouse and the Service section. The Service section holds all of the important systems, such as the Standard Payload Rack, the Nutrient Delivery System, and the Air Management System, all of which heavily regulate and monitor the plant growth to ensure success. This is a demonstration of the Eden ISS in the Arctic. It's completely functional and sustains the crew. Further, theoretical adoptions could be onto the lunar or Martian surfaces. These will need to be heavily insulated, and it's important to have a modifiable design to adapt to different situations, such as described here. Nutrient harvesting is a critical aspect of sustainability in space. Closed-loop systems are a must, and we can harvest nutrients from waste, as described from the Melissa loop. This is a loop demonstrated here. We can see that there's plants in compartment 4, which feed the crew in compartment 5, and all of the crew waste and other waste accumulated throughout the process either go to compartment 3 or compartment 1, where they're processed into the further compartments, all in a closed loop, all nourishing each other. However, they will need to be flushed eventually. More research is also required. Genetic modification is another interesting technology that is very applicable to space. We can increase edible portions and increase resilience. The government versus private space sector. The private sector focuses on for-profit missions commercializing space, whereas the government focuses on not-for-profit missions, research and development, and exploration. The money here comes from taxes, which can be seen to have budget restrictions. As well, the government has long bureaucratic processes, which can delay or slow down projects. The government also has high security clearance, so they can work on things such as nuclear technology, whereas the private sector has heavy regulations when it comes to the high security clearance topics. The private sector also focuses on things such as satellites, communications, and public launches, all things that are very profitable. The private sector does not have such long bureaucratic processes and can lead to rapid development. The total NASA cost can be broken down through its different systems as demonstrated here. As well, in this graph, it can be seen that the majority of the space budget in 2024 was commercial. Next, the regulations are important as countries and companies need to adhere to international law, the Outer Space Treaty as well. It is said that weapons are banned and no country can claim any part of space as its own. This promotes fairness and also keeps the space environment clear. There is potential gray area of regulations that have not been set up yet, so companies or countries may push what may be acceptable. The training requirements for space can be seen through the Canadian Space Agency. In order to become an astronaut, you must have exceptional physical fitness, mental fortitude, health, and have a wide industry experience. As well, you must have a minimum of a bachelor's, and this can be even better with a master's or a PhD, but it has to be in a relevant science with related experience. The European Space Agency options are also open to Canadians. So starting potentially not as an astronaut, but working in different staff positions. There is an opportunity to take the European Space Agency Academy as a Canadian, which is incredibly beneficial to university students who are looking to broaden their space knowledge, understanding, and teamwork. Space farming applications on Earth. It's important to see that space agriculture teaches us how to better use closed-loop systems and sustainable agriculture. We can address climate change and have advances in our controlled environment agriculture situations. Scientific development is a must, and space really teaches us how to use this advancement. Some applications could include such things such as the Eden ISS in emergency relief situations to produce biomedical and other pharmaceutical products. This will bring pharmaceuticals around the world with greater ease as they're able to be produced anywhere in a closed loop system. In conclusion, I want to end off with this quote from Chris Hadfield. He says, "What I did every day would determine the kind of person I'd become." And I think this is really important and applicable to horticulture because the research that we do now and the goal that we have in the end, we can reach that goal to a better sustainable world. If we work every day, much like if you want to be an astronaut, if you work every day towards that goal, you can achieve success and we can achieve a more sustainable green world. Thank you. This is the credit for the presentation template that I used. These are my references. And thank you. Have an amazing day.